On April 4th, a comet that had been travelling through deep space for nearly 2,000 years reached the Sun. It was gone in seconds, not because it hit the surface, because passing 99,400 miles above it was already close enough. But here is the part the headlines did not stay with. Something may still be out there, a faint trace of what that comet was made of, threaded through the Sun's outer atmosphere. Scientists are still checking. That matters to you for a reason most coverage never mentioned. The cameras tracking that debris are the same cameras that watch for solar storms, capable of knocking out GPS, disrupting power grids, and cutting the satellite signals woven into daily American life. Stay with me, because this story is really about two things at once. What happens when something ancient meets the Sun, and why the cameras that watched it die are the same cameras standing between you and the next major solar disruption. If this kind of careful space coverage helps you sort signal from noise, give this video a like. And if you want straight answers when the sky does something unusual, subscribe and come back. Tell me in the comments if you have ever seen a comet with your own eyes. The comet's full name was C/2026A1. If you watched the earlier video on this channel about what scientists could not predict near the Sun, this is the follow-up. That video covered the approach. This one covers what the approach left behind. MAPS was discovered on January 13th. Not by a large professional observatory, by a small team of amateur astronomers using a telescope in Chile. That matters more than it sounds. This was not some object found after weeks of headlines. It was a tiny green speck caught early by people who knew where to look, and from the start it looked different. It was unusually bright for its distance. When astronomers first tracked it well away from the Sun, it was still shining around 18th magnitude. You could not see that with your eyes, but for a comet that far out it was enough to get attention. Here is the simple version. If a comet looks lively while it is still far away, people start wondering how big it really is. Bigger comets usually hold together longer. Bigger comets can also put on a much better show. For a while, hopes ran high. Some early estimates suggested a nucleus up to 1.5 miles wide. That is a chunk of ice and rock about the length of a long walk through your neighbourhood. Big enough to make people wonder about a real naked eye event. Then came the reality check. The James Webb Space Telescope took a closer infrared look. That changed the picture sharply. The nucleus now looked closer to 400 meters across. That is about a quarter mile. Think of 4 football fields laid end to end. Still large by human standards, but much smaller than the early guess, and that smaller size changed the mood. Suddenly, this did not look like a sure survivor. It looked more like a question. Could something that size pass that close to the Sun and stay in one piece? We already knew the path was extreme. On April 4th, MAPS reached Perihelion, its closest point to the Sun. It came within 99,400 miles of the solar surface. That sounds large until you scale it honestly. The Sun is about 864,000 miles wide. So this comet did not just pass near the Sun, it skimmed just above the Sun's visible surface. The heat and radiation at that distance are difficult to put into everyday terms, but the comparison to passing the outer edge of an industrial furnace gives you some sense of the scale. It never had a chance at comfort. The Sun's radiation can boil off ice fast. Solar wind can tear material away, and gravity that close can pull unevenly across a small body, almost like twisting a cracker until it snaps. That is why Sungrazers are closely watched. They do not need to hit the Sun directly. The conditions alone are severe enough to break them apart, and often they do not survive. Astronomers had one main way to watch the final turn. A spacecraft called SOHO had been staring at the Sun for decades. Its camera blocks the Sun's face completely. That lets it see the faint space around it, and that is exactly where MAPS was heading. That camera matters because ordinary telescopes struggle near the Sun. The glare overwhelms them. It is like trying to spot a firefly next to a stadium floodlight. So for the most dangerous part of the pass, solar spacecraft become the main witnesses. MAPS entered the Lascaux C3 field on April 2nd. People watched frame by frame. Some hoped it would round the Sun, brighten dramatically, and then emerge into evening twilight. A few even started calling it the Easter comet. That hope was understandable. We have seen Sungrazers surprise us before. A few have gone in looking doomed and then returned glowing, but hope is not data. When the data finally came in, it turned against the comet. MAPS did not reappear as a healthy object. Solar monitoring reports confirmed it did not survive the close encounter. The nucleus disintegrated at perihelion on April 4th. If you only saw the quick headlines, that sounds like the whole story. Comet goes in, comet dies, story over, but space rarely works that neatly. When a Sungrazer comes apart, it does not vanish like a switched-off light. It can leave dust, it can leave gas, it can leave ionized material threaded into the corona for a short time, and sometimes the visible head dies before the tail does. That is the part people rush past. The object may be gone, the material may not be, and for scientists the material is often the more useful part. Right now, we need to be careful. There is no confirmed report yet of a strong, lasting post-perihelion tail from MAPS. Early observers are still checking. We may know more in the coming days, so let us keep the language honest. The comet's destruction is confirmed. A surviving debris display is still unverified. Some dust and gas may linger briefly, but that has not been independently confirmed yet. Here is why that distinction matters. A dramatic headline can turn a possibility into a stated fact in minutes. With solar stories especially, unverified images often drive overconfident claims. This channel works differently. What we can say is this. If any debris survived, current assessments suggest it would likely be faint, short-lived, and poorly defined. Not a dramatic torch over your backyard, more likely a subtle remnant that only careful observers could track, and even that ghost would matter, because the material from a dying sungrazer can act like a tracer inside the solar environment. It can show how the sun's outer atmosphere is moving. It can reveal where magnetic structures tug and bend. Think about that for a second. Something that began as ancient ice can become a temporary marker inside the sun's outer weather, not by intention, just by dying in the right place. MAPS also mattered because it was discovered so early. Astronomers do not often get long warning on these close solar dives. This one gave them time to watch its behaviour, compare brightness changes and test predictions before the final plunge. That early warning made the ending more important, not less. We got to see expectation collide with reality in real time, and some observers now think the warning signs were present earlier than most coverage acknowledged. The low dust output may have been one of those signs. The story also has a human side. Amateur observers across several states photographed it from the ground. Professionals modelled its tail. Spacecraft tracked it from above the atmosphere. Everyone was watching the same small visitor, asking one simple question. Would it live or die? On April 4th, we got the answer. It died. But not before forcing us to pay attention to a region of space most people never think about. A region that affects radio, satellites, navigation, and eventually power systems here on Earth. That is where this becomes your story too. If you use GPS to drive, if you depend on satellite television, if your weather alerts, banking timestamps, or emergency communication rely on space-based systems, then you already depend on the sun behaving in ways we can track, and we track it with tools that also caught MAPS. There is something else worth holding on to. This comet was not discovered by accident in the final hour. It was found by a small program called MAPS, named from the observers' surnames. They used an 11-inch telescope in San Pedro de Atacama, Chile. An 11-inch telescope sounds modest beside James Webb, and it is. But sometimes that is how astronomy works. The first warning comes from patient people, not giant machines. Then the bigger instruments move in. That handoff shaped this whole story. Ground observers first. Then Webb measured the nucleus. Then SOHO watched the fatal dive. Each step answered one question and opened another. The first answer was that the comet existed. The second was that it was smaller than hoped. The third was that it did not survive. The next question is the quiet one. Did it leave anything useful behind? And here is the detail most quick reports skipped. Webb's 400-metre estimate made MAPS roughly similar in size to Comet Lovejoy, a sungrazer that survived in 2011. That single comparison is why some astronomers still thought survival was possible almost until the end. Size alone was never the whole story, though. Some observers noted that MAPS appeared to be producing relatively little dust, compared to what might be expected for a comet at its brightness level. That observation may have bearing on the outcome, though the connection has not been formally confirmed. One experienced observer, Michael Yeager, openly wondered if the comet had developed a hard crust, or maybe it was a gas-rich object on its last legs. Those are very different pictures, and the outcome on April 4th makes the second one harder to ignore, so we begin with a death. But the death is not the strangest part. The path that brought MAPS here may stretch back nearly 2,000 years, and the evidence for that is not legend. It comes from a historian who wrote it down while it was still happening. That older story begins with the kind of Comet MAPS appears to have been. NASA calls these objects Sungrazers. To earn that name, a comet has to pass very close to the Sun at Perihelion, close enough that sunlight, solar wind and gravity all start working against its survival at once. NASA gives a rough threshold of about 850,000 miles from the Sun. MAPS came far closer than that, so close that even the word Sungrazer feels gentle. This was not a near miss. It was a deliberate dive through the danger zone. Most Sungrazers do not live through that dive. That is not dramatic language. That is the normal result. The sun strips away volatiles, Io drives violent outgassing, and pulls on the body hard enough to fracture weak spots. But MAPS was not just any Sungrazer. Its orbit points toward a famous comet family called the Kreutz group. If you have never heard that name, you are not alone, yet it matters deeply here. The Kreutz family is thought to be the leftover wreckage of one enormous comet that broke apart long ago. Not last century, not in modern astronomy. Long before any camera existed, the pieces spread out along related orbital paths over centuries. Some became famous historical comets, others vanished near the sun unobserved. What we see today are the heirs to that ancient event. Research associated with the SOHO mission suggests a large majority of the Sungrazers it has detected follow this same orbital path. That tells you how dominant this family is. It is like a well-worn road through a hostile region. Most travellers who take it do not come back, so MAPS may have belonged to this same family. If so, it was one fragment in a chain that includes some of the most dramatic comets ever recorded, alongside many that vanished without fanfare. This is where the story gets larger than one lost comet. If MAPS was truly a Kreutz fragment, then yesterday's event was not random. Under the Kreutz family model, it may have been one event in a chain of fragment returns stretching back many centuries. That framing comes from orbital research, not confirmed history. We need to slow down here, because once you think in those timescales, the sky starts feeling different. The object that died yesterday may have last passed through the inner solar system before the rise of modern nations, before telescopes, maybe before the first draft of many familiar histories. Recent orbital work suggests MAPS may have last passed through the inner solar system roughly 1,700 to 1,900 years ago. That estimate carries real uncertainty. Treat it as a range, not a precise date. But even a rough range puts the previous passage somewhere in the late Roman world. That is close enough to raise serious eyebrows. Then comes the remarkable historical link. Astronomer Zdeněk Sekanina, whose work has been affiliated with NASA's Jet Propulsion Laboratory, suggested MAPS might be related to a comet or group of comets seen in broad daylight in the year 363. The ancient source is Ammianus Marcellinus. Let that sink in. Not seen at dawn, not seen after sunset, seen in broad daylight. Now, we need honesty again. This historical connection is not settled beyond doubt. It is a research-based scenario, not a courtroom verdict, but it is grounded in real orbital work and real ancient writing. It deserves care, not mockery. Ammianus Marcellinus was a Roman historian of Greek origin who wrote in Latin. He lived close enough to his era to matter as a witness. In his account, he made a brief remark that comets were seen in daylight in late AD 363. That tiny line has fascinated comet researchers for years. Why? Because daylight comets are rare, very rare. To be seen with the naked eye while the sun is up, they need to be extremely bright, very well placed, or part of an unusual display. You do not casually forget a sight like that. Sekanina's 2022 study explored one possible explanation. He tested a scenario involving not one daylight sungrazer, but a swarm, 10 sungrazers, visible in the daytime, all reaching perihelion over about 4.6 days. 10, over less than a week. If that sounds almost impossible, remember what a fragment family means. It means once there was something much larger. And if the breakup happened under the right conditions, groups of fragments could return close together. That does not prove MAPS was one of those ancient cousins. But it makes the idea scientifically respectable, and it changes something practical about how we watch the sun today. This family has been sending fragments past the sun for centuries. That means more are likely coming, and the instruments built to track the next one are the same instruments that protect your power grid and your GPS signal. Here is why this part of the story lands differently for viewers who have lived a long time. You already know that families leave traces, not always in obvious places, a name on an old photograph, a habit passed down without explanation, a letter that survives the person who wrote it. The Kreutz family works something like that, except the inheritance is orbital and the timescale is measured in centuries. When you see it that way, this comet was not a random visitor. It was carrying something old. That is the right instinct here. The death of MAPS matters. But the bigger question is what kind of family produces objects like this at all? A family that can scatter fragments across generations of human history. A family that can give one era a blazing legend and another era a failed hope. If that connection holds up under further study, then MAPS may have belonged to a fragment chain with roots going back nearly 2,000 years. Not the same object as anything seen in antiquity, but possibly part of the same family. That is why the Kreutz name matters. It gives us a framework. Without it, MAPS is just a dramatic one-day event. With it, MAPS becomes a fragment on a known route, part of a broken inheritance. Some are tiny and never make headlines, some flare up suddenly, some die in silence behind the solar glare. A few become famous enough to enter history books, but all of them carry information. And each time one passes close to the Sun, that information helps scientists calibrate the instruments watching for the next solar event that could affect life on Earth. There is another piece to remember. A family orbit does not mean identical behavior. Two cousins can follow related paths and have very different endings. One may be rich in dust. Another may be cracked and weak. One may survive. Another may shred before perihelion. So when people ask, why did MAPS fail if others made it? The family label cannot answer that alone. It tells us where the comet likely came from. It does not guarantee how it was built. Still, the family history helps explain why astronomers were excited so early. A confirmed Kreutz Sungrazer found well before perihelion is rare. Usually these things brighten only when they're already buried in solar glare. MAPS gave observers time to model, time to compare, time to imagine. And imagination matters in astronomy, as long as it stays tied to evidence. When experts saw the orbit, they naturally reached backward. They thought about the great comet of 1843. They thought about Perihelion. They thought about Lovejoy. They thought about older returns we can never fully reconstruct, not because they wanted a fairy tale, because this is how comet science works. Every new fragment gets compared to the archive. Every era saves what it can. Ionized gave us a sentence. 19th century observers gave sketches and timing notes. We give coronagraph movies and infrared data. The tools changed completely. The feeling did not. People looked up. They saw something impossible near the Sun. They tried to make sense of it before it disappeared. There is a good reason the ancient daylight report remains powerful. It reminds us that some comet events are visible not because people went searching, but because the sky forced them to look. A daylight comet breaks through ordinary routine. It interrupts the day itself. MAPS did not do that, not for the public. It died before it could become a shared visual event over towns and fields. That is part of why this story feels unfinished. It promised public wonder, then retreated into specialist imagery. But sometimes the less obvious event teaches more. A failed Sungrazer can tell us about structure, timing, and fragmentation in ways a brighter survivor cannot. Failure is data too. There is also a humbling lesson here. The solar system often appears orderly from a distance, but Sungrazers demonstrate that even within well-documented orbital families, outcomes remain uncertain until the final hours. The Sun is not a neutral environment. It is an active force that tests every object that passes through. MAPS came from a family famous for brushing that judge. Yesterday, the verdict was harsh. But here is what that family history actually tells us about why MAPS lost. Two comets can share the same ancient road and have completely different endings. One survives, one dies, and the reason usually comes down to something invisible, something hidden inside the nucleus that no telescope can measure in advance. If Sekanina's historical model continues to hold up under scrutiny, then the fragment family this comet belonged to may have been producing observable events since classical antiquity. That is a working hypothesis, not a confirmed conclusion. But it is grounded in real orbital modelling and real historical records. That context changes how the word debris reads in this story. In the technical sense, debris means material released after breakup. In the broader Kreutz family context, each fragment may also carry information about an ancient original body. That is a scientific interpretation, not a certainty, but it is one researchers take seriously. So when we say MAPS may have been a fragment, we mean this object may have been one piece of a much larger body that broke apart near the Sun long ago. A piece that spent centuries in deep space before returning, only to come apart under modern observation. That is a striking idea. And a scientifically useful one, because knowing where a comet came from does not tell you how strong it is, and near the Sun, internal structure may be the deciding factor. Lovejoy in 2011 was estimated to be in a similar size range as MAPS. Both were Kreutz Sungrazers, yet one emerged and one did not. The answer to why may come down to something that was already visible in the weeks before perihelion, something most coverage walked right past. That comes down to structure, heat, and timing, not romance, not luck alone. A Sungrazer lives or dies by what it is made of, how fast it sheds material, and how violently the sun forces it to react. Comets are often described as dirty snowballs. That helps children start, but for adults it can hide the real picture. A comet nucleus is not a neat ice cube. It is a rough mix of ice, dust, rock, voids, cracks, and weak layers. A comet nucleus is roughly like a frozen mix of gravel, dust, and trapped gas, with empty pockets and uneven layers throughout. When sunlight warms it unevenly and gravity pulls across its width, those weak points come under stress. That is where the failure usually starts. As a comet approaches the sun, buried ice begins turning directly into gas. That outflow drags dust with it. Jets can erupt from active patches. If those jets push unevenly, they act like tiny thrusters. That may sound small. It is not. A steady, uneven push can spin a weak body faster and faster. And if the nucleus is already fractured, rising spin can tear it apart before gravity even gets the last word. That exact possibility came up with MAPS. In the new web-based work, Qicheng Zhang and colleagues argued that the smaller nucleus size did not rule out survival, but they also warned that strong outgassing could spin the nucleus up and break it apart before or during the near-Sun passage. So even after Webb reduced the size estimate, survival was still on the table, not because the comet looked safe. Because we have seen a similar-sized Sungrazer beat the odds before. That earlier comet was Lovejoy. Lovejoy reached Perihelion in December 2011. It passed about 87,000 miles above the Sun's surface. That is closer than MAPS came. On human scales, that sounds enormous. On solar scales, it is a razor-thin pass. Most people expected Lovejoy to die. Many scientists did too. Instead, it emerged. Damaged? Yes. Destined to fade later? Yes. But it survived the pass itself, and for a brief time it became one of the great solar science gifts of its decade. Here is the difference. Lovejoy seems to have had enough structural integrity, at least briefly, to keep a core together through perihelion. MAPS did not. Something in its build, activity, or stress history gave way. That may have happened right at perihelion. It may have started earlier. Some observers already suspected trouble before the final turn. Rapid brightening followed by odd plateaus can sometimes hint that a nucleus is becoming unstable. Not always, but sometimes. Observers tracked this uncertainty well before the pass. The comet brightened quickly at one point, then stalled. Its coma changed size. Its core seemed to compact, then behave less convincingly. Those swings kept forecasters guessing. A healthy comet can vary. A dying comet can also vary. That is the problem. Brightness changes do not come with labels. There was another clue. Michael Yeager wondered why MAPS seemed to be producing so little dust. That matters because dust is the part of a comet that reflects sunlight well and builds a crowd-pleasing tail. Gas can make a comet active without making it visually grand. If MAPS really was low on dust, that could have been a warning. The comet may have looked chemically lively, while still lacking the sturdier, brighter output people hope to see later. A structure can look solid until the right combination of stress arrives all at once. A hidden weakness that held for years can decide the outcome in a matter of hours once conditions exceed its limit. That appears to be what happened with MAPS. That may be the best everyday way to picture MAPS. The comet was not a solid cannonball. It was a stressed ancient fragment facing an impossible crossing. On April 4th, the structural limits of MAPS appear to have been reached. But here is what most people miss entirely. The way a comet dies tells scientists something that a healthy survivor never could. A body that breaks early may be more porous. A body that sheds dust differently may have a crust. A body that spins itself apart may have strong jets and weak cohesion. We still do not have all those answers for MAPS. Some will require more analysis, some may remain uncertain, but even uncertainty has layers. Scientists will ask whether the breakup was thermal, tidal, rotational, or a mix. That matters because those are not identical deaths. Thermal breakup means heat tore it open. Tidal breakup means gravity pulled unevenly across the body. Rotational breakup means the spinning jets finished it. In reality, all three may have arrived together. Heat softened the weak spots. Jets pushed unevenly. Gravity tugged. Then the structure crossed its limit, and once that happens, the sun does not need to do anything more. Now the comparison that matters most is Lovejoy. Scientists studying Lovejoy found that its ionized tail responded to the structures around it and acted like a tracer for the sun's magnetic field near the corona. That is a beautiful phrase, tracer, because it turns a comet from a spectacle into a tool. Lovejoy's tail carried ionized gas. Ionized gas responds to magnetic fields. So as the tail bent and wiggled, scientists could read the invisible structures shaping it. Scientists use a similar technique in Earth's upper atmosphere, releasing tracer clouds to study airflow that would otherwise be invisible. A comet's ionized tail near the Sun can serve a comparable function. The material responds to the magnetic structures around it, making those structures briefly visible through their effect on the tail. That is why MAPS still matters after dying. If even a little ionized material lingered after breakup, it may offer a tiny version of the same opportunity. Not guaranteed, not confirmed yet, but scientifically worth checking. This is also why the backyard question is only half the story. Yes, it matters whether you could see it from your yard. But here is the other half. If even a thin trace of MAPS lingered inside the corona after the nucleus died, scientists may have gained something more useful than a bright sky show. They may have gained a moving record of conditions in a place we cannot visit. That record could improve how we read the next solar eruption headed toward Earth. We should also remember another famous failure. Comet Ionized in 2013 approached the Sun with huge publicity. Many hoped for a major display. Instead, it broke apart. That disappointment still shadows every bright Sungrazer forecast today. MAPS walked right into that history. Some people saw a future Lovejoy, others feared another Ionized. The trouble is that both comparisons made sense. This is where comet forecasting becomes humbling. You can estimate size, you can model tail geometry, you can study family history, you can compare past Sungrazers, then the Sun gets the final vote anyway, and the vote can change late. Optical engineer Nicolas Lefaudieu made a key point before Perihelion. He noted that dust released between roughly 6 hours after Perihelion and the next several days would largely determine the later tail's length and brightness. That is a small window, but a decisive one. So if MAPS's nucleus failed at the wrong time, the bright public show was lost. Not because the comet had no material at all. Because the release history did not favour the kind of post-solar display people wanted. That is a subtle point, and it explains many public misunderstandings. A comet can be real, active, and scientifically important while still failing to become a big twilight spectacle. Tail brightness depends on geometry, dust production, survival timing, and sunlight scattering. It is not a simple reward for effort. There is another detail people miss. A comet near the Sun can appear promising because of viewing geometry, not because it is about to become legendary. The line between good chance and great comet is much narrower than headlines suggest. That is why calm coverage matters. If you were hearing wild promises last week, yesterday probably felt like a letdown. If you understood the physics, it felt like one plausible ending among several, and one very informative ending. MAPS also reminds us how much Webb changed the conversation. Without that 400-meter estimate, expectations may have stayed inflated longer. Webb gave us a smaller, more realistic nucleus size, and that helped frame the risk. It did not settle the outcome, but it narrowed the honest range. That is real progress. Science is not just about heroic discoveries, it is also about taking something mysterious and making the uncertainty more precise. By the time MAPS entered the coronagraph fields, the debate was no longer dreamy. It was sharp. Could a Lovejoy-sized body with strong outgassing and low apparent dust make it through? April 4th answered that in the negative. Still, the last chapter may not be written. A nucleus can die while debris keeps speaking. A visible head can fail while dust streams onward briefly. That is why observers are still watching the aftermath, and what they are watching with changes everything about why this comet mattered to people who never planned to look for it. But here is the part most early coverage skipped. The cameras that watched MAPS were not built to watch comets at all. They were built to monitor solar activity that can affect systems people depend on every day. Understanding what those cameras actually do changes why this event matters. Start with the word coronagraph. It sounds technical, but the idea is simple. A coronagraph blocks the bright face of the Sun so we can see the faint outer atmosphere around it. In everyday terms, it creates a tiny artificial eclipse. That is the trick. Without blocking the Sun's glaring disk. The corona disappears in the light. With the disk blocked, a hidden region comes into view. Streamers appear, eruptions appear, and sometimes so do comets. SOHO has long been one of the masters of that view. Its LASCO instrument is actually a set of coronagraphs with different occulting disks, so scientists can look at different distances from the Sun. That is how MAPS could be followed through the most dangerous part of its path. This is not just an astronomy bonus, it is a space weather necessity. The corona is where huge magnetic bubbles of plasma can erupt. Those are coronal mass ejections, or CMAs. When they head toward Earth, they can affect radio communication, satellites, navigation signals, and power grid operations. So the same tools that tracked MAPS also serve as part of the monitoring network for those events. Here is the part most coverage skipped. NOAA's new CCOR-1 coronagraph is built to feed Earth impact forecasts, not just pretty pictures. NOAA says information from CCOR-1 will go into the WSA NLIL model used to forecast CME and solar wind impacts on Earth. That is a big step, not dramatic in the movie sense, important in the real sense. CCOR-1 rides on GOES-19 and watches the corona every 15 minutes, not once a day, every quarter hour. Think about what that means if a solar eruption is building. By the time your weather alert goes off, that camera may have already spotted the disturbance an hour earlier. That is not a small upgrade. For anyone who depends on stable satellite signals or clean power, it is the difference between a warning and a surprise. NOAA also points out something charming and practical. Because CCOR-1 is closer to Earth than older coronagraph viewpoints, the Moon can drift through its field. Earthshine can affect the images too. Around the equinoxes, reflected sunlight from Earth can create problems. That means not every odd streak is a discovery. Not every shape is a mystery object. Sometimes it is the Moon. Sometimes it's reflected light. Sometimes it is an instrument artifact. That simple fact is worth gold in an age of overreaction. SOHO's official documentation makes the same caution plain. Coronagraph images can show planets, stars, and comets. They can also show high-energy particle hits, dust, or instrument artifacts. In other words, careful reading matters. And older viewers tend to appreciate that. A mature eye knows better than to trust the first dramatic interpretation. That instinct serves you well here. SOHO itself was never designed to become the greatest comet hunter in history. It launched in 1995 to study the Sun and its outer atmosphere. Yet because its coronagraphs could see near-Sun space so well, it started catching comets that almost nobody else could see. By early 2024, SOHO had helped discover its 5,000th comet. Let that number settle in. 5,000. More than half of the comets known today have been discovered using SOHO data. That is astonishing by any standard. It is also a reminder that major discovery often comes from patient, repeated watching. Not one heroic night, years of steady observation. That is worth holding on to. Ordinary people, working carefully, help turn a solar mission into one of the most productive comet-finding efforts in history. One of them, Hanji Tan, found the 5,000th SOHO comet after years of searching. Tan had been participating in the Sungrazer project since age 13. He later described the experience of seeing comets approach the Sun for the first time as deeply meaningful. It is hard to find a better sentence for why astronomy still matters, and it connects directly to MAPS. Because MAPS also began with attentive people using modest tools and disciplined watching. Then bigger systems took over. That handoff between amateur skill and professional infrastructure is one of the healthiest things in modern astronomy. The Sun does not care who noticed first, but science benefits when many eyes are involved. There is another reason comets and coronagraphs belong together. Research published in connection with the Lovejoy mission found that Sungrazers can briefly act like natural solar probes. Lovejoy's ionized tail lets scientists trace motions in the corona, similar to how researchers release tracer clouds in Earth's upper atmosphere to study winds that would otherwise be invisible. So a comet near the Sun is not only a victim. Briefly, it becomes an instrument. Not a designed instrument. A sacrificial one. That is a hard image to forget. A piece of ancient ice racing inward, then turning into a temporary line of evidence inside the corona. It burns, it fragments. But in doing so, it reveals the invisible. This is why the possible debris from MAPS matters so much, even if it proves faint. If material survived breakup long enough to show structure in the corona, it could help refine how we read that region. Again, careful language. Could, not did. Scientists are still checking. Current assessments suggest the visible aftermath, if any, would likely be faint and short-lived. Researchers have discussed scenarios ranging from no visible remnant at all to a sockled headless comet, where the nucleus dies but a dust tail briefly lingers. Yesterday's outcome leans toward the dimmer end, but follow-up matters. This is also where the older spacecraft and newer spacecraft meet. SOHO is aging. NOAA openly notes that CCOR-1 is designed to replace the aging LASCO chronographs over time, yet right now, both perspectives help. That overlap is valuable. It is like listening to an experienced old weather station while a new radar comes online. You do not throw one away the first day. You compare, you learn, you build confidence. And confidence is what space weather forecasting lives on. But here is the connection most people never make. A dead comet and a solar storm that knocks out your GPS signal are watched by the same camera. They live in the same neighborhood, and what scientists learn from one can sharpen how they read the other. That is not a side note. That is the whole point of why this comet mattered to people who never planned to go outside and look for it. MAPS crossed that overlap dramatically. It entered the field where solar scientists watch the corona for Earth-relevant activity. Its death did not threaten Earth. But the tools watching that death are part of what protects the systems you use. That is the real practical bridge. If you live in a rural area and depend on satellite communications, this matters. If you are retired and travel by RV with GPS, this matters. If you still use shortwave, aviation radio, marine systems, or just want your bank time, map apps, and weather alerts stable, this matters. We all live under space weather now, whether we think about it or not. And comets help remind us of that because they turn the invisible visible. There is one more overlooked lesson from the chronograph world. The sun's outer atmosphere is not empty space. It is structured, dynamic, and full of flow. Streamers can last for months. CMEs erupt like giant magnetic bubbles. Solar wind streams outward continuously. So when a comet enters that region, it is not crossing a blank black backdrop. It is entering weather. Not weather you feel on your skin. Weather that shapes the space around Earth. That is why the phrase "just a comet" does not hold up near the sun. At that distance, every object becomes part of a dynamic environment. Nothing passes through that region without leaving a record. MAPS gave that interaction to us in real time. Webb measured it before the end. SOHO watched the final turn. NOAA's new coronagraph era is opening at almost the same moment, and somewhere in all that data may be a better understanding of how fragile solar visitors behave under extreme stress. So the comet is gone. That part is settled. But here is the question the instruments are still trying to answer. When the nucleus broke apart, did it leave anything inside the corona that we can actually read? The answer changes what this event is worth, and it depends entirely on a detail most coverage never mentioned. What should we watch now, first? The honest answer: we may see very little. A disintegrated Sungrazer does not owe us a farewell show. Sometimes the end is mostly for the instruments, not the backyard observer. Still, there are a few specific things worth following. Scientists and skilled amateurs will keep checking chronograph imagery for any coherent remnant. They will also look for signs that dust or ionized gas persisted after the nucleus failed. We should be clear about one thing right now. There is no confirmed report yet of a strong lasting post-perihelion tail from MAPS. Early observers are still checking. That distinction matters. A dramatic headline can turn a possibility into a fake certainty in minutes. This channel will not do that. If something remains, it may appear as a weak, poorly defined tail or streamer. And there is one last possibility we need to respect. In some Sungrazer scenarios, a tail can outlive the nucleus by a meaningful interval. Sekanina's 2022 study discussed how post-perihelion tail development could affect visibility in historical Sungrazer events, including the AD 363 scenario he modelled. That does not mean MAPS will repeat that behaviour. It means comet death and comet visibility are not always the same clock. So in the next few days, the question is not, did the nucleus live? We know that answer. The question is, did enough material survive in the right geometry to remain detectable? That is a narrower question. A better question. If you are hoping for a broad public spectacle, keep your expectations low. Current assessments suggest any debris display would likely be faint and short-lived. That is not pessimism. That is proportion. But faint does not mean unimportant. A faint remnant can still help scientists test breakup timing. It can help them judge when the nucleus failed. It can help compare pre-perihelion and post-perihelion dust release. It can also help refine the next Sungrazer forecast, and there will be a next one. That is how this field advances, not by one perfect comet, by stacking many imperfect cases together until patterns sharpen. We also still do not know exactly when MAPS lost structural coherence. Did it begin to fail well before the closest turn? Did the final breakup happen right at perihelion? Or did the nucleus survive the deepest moment only to collapse immediately after? Different datasets may answer that differently at first. So this part is still developing. You deserve that plain answer. There is also the larger unknown of family history. The Kreutz connection looks strong. The exact relationship to older members remains under study, and the suggested tie to the daylight comets reported by Ammianus Marcellinus is fascinating, but still a scientific reconstruction, not a finished verdict. I want to linger on that because trust matters. A good science channel should let mystery stay mystery when the evidence is not complete. We do not lose anything by saying, this part is still being worked out. In fact, we gain credibility. Now, if you want one practical thing to do after this video, here it is. Follow NOAA's Space Weather Prediction Center and the SOHO coronagraph imagery over the next several days. If there is a real remnant, that is where serious observers will be looking first. You can also keep an eye on updates from NASA solar pages and reliable astronomy outlets that correct themselves when new data arrives. That correction habit matters. Fast stories go wrong, trustworthy sources revise, and if you simply enjoy the sky without chasing every image update, watch the western twilight with modest expectations. I mean modest. If any debris becomes visible from the ground, it will probably be subtle, more ghost than beacon. This matters especially for viewers who remember brighter public comets from earlier decades. You know the difference between a comet the whole neighborhood notices and one you need careful instructions to find. MAPS now looks much more like the second kind, if it shows anything at all from the ground. There is a deeper reason to stay with the story anyway. MAPS gave us a clean example of how modern astronomy really works. Discovery by small teams, measurement by major telescopes, verification by spacecraft, revision as new evidence comes in. No fake certainty, no shame in changing the call. That process is not a weakness, it is the strength. Yesterday's event also reminds us that the sun is not scenery. We talk about it every day as if it were a familiar lamp, but the region just above it is violent, magnetic, and unforgiving. A comet can spend centuries reaching that threshold and then lose itself in hours. Think about that scale. A traveller from deep time erased in an afternoon, and yet not fully erased. Because the record remains, in images, in models, in brightness curves, in the question of whether a debris trace still threads the corona. In the broader family history stretching behind it. That is what the title really points to, not some hidden conspiracy, not a secret object, something quieter. The possibility that the most important thing MAPS left behind was evidence. Evidence in the sun's outer atmosphere, evidence in our instruments, evidence in the comparison between promise and outcome, evidence in the continuing story of the Kreutz family. If you are the kind of viewer who likes neat endings, astronomy can be frustrating. The comet died, but several questions lived. That is normal. Often, the best space stories end with better questions than they began with. What remains unknown is simple to hold. We do not yet know what the comet left behind. We do not know exactly when the nucleus gave way. And we do not know how firmly this object fits inside the long chain of Kreutz fragments that may reach back to ancient eyewitness accounts. Those answers will come slowly, not in a single headline. That is how honest science actually moves. A traveller from deep time, erased in an afternoon. But the record of its passing is still being written. The comet posed no threat to Earth. But the instruments that tracked its death are part of the same monitoring network that watches for solar disturbances that can affect GPS navigation, power systems, aviation routes, and the satellite signals woven into daily American life. If any of those systems matter to you, this story was already about you. And if you're simply someone who steps outside after supper and looks west, it matters in a different way. The sky is still capable of surprises. Not always the bright kind, sometimes the quiet kind, the kind that rewards patience. That part is still moving, the instruments are still running, the archive is still growing. For now, watch the coronagraph updates and trust the sources that revise carefully when new data arrives. If a faint ghost of MAPS appears, it will come quietly. If it does not, the story still matters. A Roman historian saw daylight comets and wrote down his astonishment. In April 2026, we watched one more piece of that same old family meet the sun under modern cameras. Same sky, different tools, same feeling of watching something rare pass through. Take care of yourself. Keep looking up. I will be here for the next one.